Welcome to the second instalment of the organic videos, looking at synthesis questions from the Olympiad papers. In this video we're going to look at the start of question 4 from 2012. So let's scroll through and from the 2012 question, here we go. Now we're looking at overall synthesizing this chemical Lipitor, and here it is here, and it's going to be done via a huge reaction using lots and lots of different steps, but helpfully the Olympiad question setters have broken it down, and you can just hear the phone going off in the background. I'm hoping someone will answer that. But here's the first start of, or the first bit of the synthesis. Sorry, I've been put off by the phone going off. And so I chopped it up a little bit, and so here you can see we're turning compound A, which has got two alcohol functional groups and a chlorine, into G, which is a much larger chemical. It's got 7 carbons in. Here we've actually only got 3. So we're going to be using a variety of chemicals to build up that carbon chain, and unsurprisingly we're using sodium nitrile. So CN, which is often used in organic chemistry as a nucleophile, and here we have CN minus with its lone pair on the carbon, and that would come in and attack that carbon there, and the chlorine would break off. Now that would produce compound B. So if I just draw B here, I'm just hoping we've got enough room on this page, and this is the worst stylus I think I could have possibly bought. And we've replaced the Cl with the Cn. Now Cn is always or often used in organic chemistry to build up carbon chains, and if we then heat up this chemical in acid, and unsurprisingly here we had heat in H3O+, we're turning our nitrile functional group into a carboxylic acid. Now that's not covered on the OCR A-level course, but is frequently asked about on the Olympiad. The rest of the molecule here is untouched, but we've turned our nitrile into our carboxylic acid. So that is compound C. Now, in the next step, we produce a cyclic compound. So we need to form a ring structure, and we're going to lose water in this reaction. And you can see in our molecule we've got a carboxylic acid functional group, and we've got 2 separate alcohol functional groups. Now I hope that you know that carboxylic acids and alcohols react together to form esters. So our cyclic compound D is going to be an ester. So the question you've got to be asking yourself is, will the acid here react with the alcohol on the end, or with the alcohol in the middle of the chain? The actual answer is that it will react with the alcohol on the end of the chain. We will lose this OH, we'll lose that H, and that O here will bond directly to that carbon here, which will make a ring of 1, 2, 3, 4, 5 atoms. So if we just make that now, so we'll form, here's our ester, so the carbon oxygen double bond we'll keep at the top down to O. Now that O, which is actually the O on the very end over here, it's quite tricky to explain, is then bonded to one carbon, a second carbon, a third carbon, then back to the original carbon oxygen double bond. It's quite difficult. I can actually hear a phone conversation going on very loudly, so I apologise if I seem a little bit distracted. And what you will also see is that if we take this carbon oxygen double bond here, if we go 1 carbon then 2 carbons, you've got an OH. So 1 carbon, 2 carbons, there's our OH. And that is compound D. Now that compound D is this cyclic here. And they take this and react it with a substance HBr. And you might be wondering what happens at this point. But as with a lot of syntheses, if you get stuck at a point, look ahead and see what's coming. See what other reactions are going on, because that will give you a clue about what might be in E. Now, to turn E into F, we have C2H5OH, ethanol, and an acid, H+. Now, we often add an alcohol and an acid if we're looking to form an ester. And if we're looking to form an ester, we'd take ethanol and we'd react that with a carboxylic acid. So E needs to contain a carboxylic acid. And the only way E can contain a carboxylic acid is if we break the so I've lost my thread. If we break the cyclic compound, okay, the ester, we break it here. Okay, now bearing in mind HBr will be contained in an aqueous solvent, so we will form, well, we're going to break it there. So here's my carbon-oxygen double bond, down, then up to the OH, then down and then up. Now at this point we're using HBr, and I need to have a carboxylic acid because otherwise my esterification in the next step won't work. And we're told that this is the formula of our molecule. So the only place for Br that can feasibly go is there, and that will be E. So let's do our esterification. The alcohol here is going to add on to our acid over there, so we'll keep our Br, okay, then up, OH, carbon oxygen, there we go, down, O, and then there is the ethyl group added on to form the ester, and that will be F. And here we're told NaCN. Right, where have you seen NaCN used? We saw it used right at the start up here, and the CN replaced the halide. Again, we've got our halide here, so G is going to look exactly like F, but with CN instead of the Br. So if we stick the CN on, CN, notice that I have the carbon bonded to the chain, not the N. I don't know why there's a massive arrow there. Who knows? It's not highly important. I don't even know how to get rid of it. And that is G. Maybe I should actually learn how to use this program on a slightly more sophisticated level than I do already. So here we go, we've made G. Now you'll also have seen in the question, and something I've entirely ignored up until now, they ask us about infrared bond stretching, and actually some are, I think, are bends. But they give us some absorptions, and they ask us to identify the bonds which have caused these absorptions. Now here we have 3,300, and that's seen right in the very first chemical. Okay, it's seen in B, it's seen in C, and hopefully you'll realise, and probably you'll actually know from what you've done in your organic lessons, that that will be an OH stretch. And I'm going to change colour just so it's a bit more visible. Now we have our carbon oxygen in a small ring. Well, we've got a small ring in D, so D has a absorption of 1775, and that's the one we don't know. So 1775 goes in there. 2250 to 2275. Well, that actually crops up in G. It actually crops up in B as well. So hopefully, as you can see, we use it in this chemical and in this chemical down here. That means it will be a CN stretch. NH, we don't actually have any NH bonds in any of our molecules, so that must be used later on in the question, and we could come back to that, hopefully, if I remember. And then 1700 to 1740, well, that crops up, you can probably do this off the top of your head, but it certainly crops up in G and F and in E, and that will be a carbon-oxygen double bond stretch. And that concludes part 1 of answering this question. Hopefully I'll work out how to use the program a little bit better in time for part 2.